Hello, everyone. Today is day 23, I believe, of coding every day. So, yesterday we did k closest points to origin, which we used a min heap. Today, so right now I'm just kind of alternating between backtracking and min heap. So, I think today we'll do a backtracking problem and we'll look at subsets 2. I have looked at this one before, but I haven't tried solving it yet. Alright, so you are given an array nums of integers which may contain duplicates. Return all possible subsets. The solution must not contain duplicate subsets. Okay, let me just see what the difference is between subsets 2 and subsets 1. I think subsets, does this one have, say, no duplicates? Yeah, unique integers. Honestly, I'm not really sure how this is gonna change the solution. Yeah, I know last time I did permutations, I said I was gonna look at how they make sure that there's no duplicate solutions, and I kind of forgot to do that. Or I think I looked at it, but I didn't. Yeah, it's something I should definitely look into. I guess for now I'll just use the sorted thing. So honestly, I don't really know how this is going to be any different than my solution to subsets 1. Maybe I'll figure it out as we go. But so if you think of it like a decision tree, so here's our starting point. So that's empty list. So we can either add so I guess for every elements we either add it or we don't. Right? So for the first element, so we have 1, 2, so we have empty list, and then we're looking at 1, 2, 3. So we either add it or we don't. So I equals 0. So there's only 2 branches actually. So if we have 1, 2, 3, one of them is 2, 3, where we do not add it, and one of them is 1, 2, 3, where we do add it. Okay, so that's I equals 0, and now I equals 1. And we say for each of these, we either add the position at I or we do not. So let me draw this a little bit better. So at this position, we either add it or we do not. So let's say we do not add it, then we just have 3. If we do add it, we have 2, 3. Here, if we do not add it, we have 1, 3. And if we do add it, we have 1, 2, 3. And we continue this until we hit, until I basically. And that should give us every possible subset. But so we have, okay, so we have duplicates though. So that means we'll have repeated subsets. So I think the tricky part of this problem is how do we make sure. So first I'll just code up this just to have a skeleton and a baseline, and then we can go off that. All right. So I'll make a function called DFS, which takes in well, at every step we need to know like nums and I. Okay. So, and then we want to say for Well, honestly, I think what we want to do is just call DFS. So if we say nums.pop_i, let me see the runtime. Is it times n? Yeah. So if we pop it, so this would be like doing the recursive without. So calling it again without I is equivalent to this path here. And then we also want to, so we want to insert into I position whatever we popped, I guess. Can we just call it beforehand? So could we say DFS of nums I plus 1? So that would be like the right path. And then can we say DFS of and then can we maybe like pop it like nums.pop_i? I think what I want to do instead is I always do this splicing method. I don't know if this is like slower, but to me it just makes more sense to just basically have a copy of the list without I in it. So instead of popping it, it would be like this. I mean, could we say this? Like, no. So this will be the right path of this decision tree where we keep it. So we basically just call it again, and then call it again, and then call it again. And then we want to say if I equals, whenever I is greater than the length of the original nums, I mean, I could store that in a variable. Wonder if there's a better way to do this. Like, can we start I from here and then just keep going down until it equals 0? So we could say DFS nums, and then I would be equal to length of nums minus 1. So this would give us a last, and then it would go down to this one. So I think that would, and then if we just say if I equals -1, then we want to return out of that. What do we want to return? So when I is -1, we want to, I guess we could have a result, and then we want to append a copy of nums. Okay, so in this case, I will start as 2. So then it will call so it'll either So when it calls it again, it will keep nums and I will go down by 1. So it either keeps nums or gets rid of I. Okay, let's see here what our output is. Oh, I forgot the return statement. Okay, so we don't need that, and we probably don't need that either. Okay, so we forgot a colon here. So this was indexing one value and it was trying to concatenate a list to an integer, but we want to concatenate a list and a list. So this colon will do that. Okay, so it looks like that we have what we're looking for. Okay, so now it's the age-old problem of how do we make sure that there's no duplicates. So I always do this. So I say if sorted nums.copy not in res, then add the sorted one. But this is worse than this. Time complexity is worse. So I think I'm missing something because I'm basically solving all of the problems the exact same way. And I think with this problem, there's supposed to be some tricks. There's supposed to be, like, the hard part is figuring out how to do it in linear time, but I'm doing an n log n times 2 power n. Okay, so yeah, so for this one, I'll definitely, I have to fully understand the solutions and stuff, and I don't really want to count this as a solved problem for this episode. So let's look at one more for this episode. We'll do a priority queue heap problem. And then when I do word search next time, or maybe I could just revisit in my free time these problems and figure out the right way to do it so that there's no duplicates. Okay, but for this episode, we'll continue with heap and priority queue. So task scheduler, I have seen this one before. It did look kind of confusing. So essentially, you're given these tasks and a number n. So you can't repeat the same letter. So every cycle, you can like output a letter, but you can't repeat the same letter until n cycles have passed. So we can see like x, x, y, y, n equals 2. So you can do x, that's one cycle, y, cycle 2, and then you can't do anything on the third cycle because you need at least 2 cycles between all the x's and all the y's, and it's only been 1 cycle since the last x and 0 cycles since the last y. So then you go x and then y. So normally it would be fine if there were no duplicates. You could just output them in whatever order. So the problem here is the duplicates. So if we have x, x, y, y, n equals 2, and then what's the runtime here? The size of the input array. So basically linear with constant space as well. It is a heap and priority queue problem. I don't know if heapifying this would help at all. So if I print I've never used this on strings before. Oh, whoops. This returns none, but it still should work here. So let me just experiment a little bit with how this works. So if I have like A, C, B, I'm guessing it'll just kind of... Alright, what if I have A here? Will it push the A to the front? Yeah, okay. So it does heapify it, where the lowest characters are... That makes sense. So it might be something like getting the counts of each one. So, like in the first example, where tasks equals x, x, y, y, we can basically simplify that so we know we have 2 of the same type and 2 of another type. So maybe if we put these counts in a heap, and we can do something there. And if we look at A, this color is a bit hard to see. Sorry about that. Let me turn on my brightness. If we have A, B, C, then we know it's basically 3, 1, 1. We know n equals 3. So these 3 can all be removed. Man, this is tricky. I don't really... Nothing's jumping to mind on how to solve this for me. I'm thinking like how I would do it is I'd start with the letter that has the most. I'd probably start with the letter that has the most. And then maybe the second most. Maybe this is where the heap comes into play. So if we had like A, B, B, C. So I'd start with the letter that has the most, and then maybe the second most. And then n equals 3. So maybe we just repeat that every 3 times. We just like get whatever has the most. So maybe our heap can be, so if we have like a max heap, and every element of the heap would be an array or a list, an array of size 2, and it would be the counts, and then like what character it is, maybe. So something like 3A, 2B. All right, so then we'll pop it. Yeah, and then we want to go to the second most. So we'd pop this all together. And then we'd go to the second most, and we just like keep doing that until n is, we've done n, and then we would just do that again. And then if there's nothing left to pop, then that means we add like the remaining n to our answer, perhaps. Okay, so let's try figuring that out with the test cases here. Okay, so our heap for this one, our max heap, would be 2x and 2y. So n equals, I'm going Halloween theme, I guess. So n equals 2. So we're going to pop this, and now n equals 1, right? And we keep going until all of them are 0. Okay, so then that is now 1x. Then for our next pop, it has to be something that we did not just pop. So it has to be in this one. So then we pop this, right? Because it would be x, y. So after we pop that, it'll be 0. I think maybe it's like after we pop it, that's when the countdown actually starts. So we pop it, and then, so we pop this, and then it's n equals 2. Then we pop this, and then it's n equals 1. And then our queue is empty. So we add, so far it's been 2 steps. So 1, 2. And then we add, so because our queue is empty, we add however many are here. That's the idle. And then we reset the queue. Or the priority queue. Now we do the same thing with this. So then we pop this, and it becomes 0. So we just like kind of get rid of it, I guess. So that means n equals 2. And then we pop this. Whoops. And n equals 1. And because we're done, then the answer is 5, right? 5. Okay, so if we look at this one, A, B, C. So our heap is 3A, 1B, and 1C. N equals 3. All right. So we pop this, and now the countdown is, so I'll just say like, so the current countdown is 3. We did 1 action, Can we pop another one? The next most max. And okay, so my question is, so when we go from this stage to the next like heap, which would just be 2A, we can't do that. Like, we can't just add it back to the heap right after we pop it, right? I mean, maybe we can actually. Maybe we could add it back. So we'll just pop it and then instantly push it back. But we'll have something called like visited, which tells us what we've already done this like end cycle. So because this isn't visited, we go to the next one and we don't count it as an action. So then we go to this one. Now current equals 2, and now that's 2 actions. And then because this is 0 now, we don't put it back. And then we pop this, current equals 1, and that was another action. Okay, so now we've been through the entire heap. Could we, like, instead, could we maybe have another heap? Because I'm wondering, how can we detect when to stop? Usually I was thinking when the heap was empty, but if we're adding back to it as we go, there might be some tricks. So we could make another heap and just like keep adding to that heap for every one of these. But that would be n log n, I think. But we could start there. Okay, so then there's one idle time, so we'll put it there. And now we go to this heap. So C gets reset to 3 after we pop that. So that's one action. And now we've been through this whole thing. So we add 3. And now our new heap is 1A. So our final action is we do this, and now it's 0, so we just stop, and we get 9. Alright. So I think what I want to do is like get count of every number. And I don't think we can do it with a dictionary, because similar to the other problem we did yesterday, there could be duplicates. So I feel like getting the count of every number is tricky. So we could have a list of zeros times 26. This will just be like a dictionary, I guess. So what is it? Capital letters, uppercase English character from A to Z. So we could say letter counts, and then we can say for task in tasks, print ord of task, and just return 0. So my idea is this will just be sort of like a dictionary with the counts. So capital A is 65. So I think we want to say print ord of task minus ord of A. And I think this will be the index that we want. So 23, 20, yeah. Alright, so we'll say, I guess we could just say index equals like that. And then we can say letter counts of index plus equals 1. And then when we're done, if we print letter counts, it should give us 2 at in, yeah. Alright, so this basically gets us the counts in linear time. So then when we build our heap, And I guess we could say like letters. I mean, at this point, I should just have a dictionary, right? Yeah, I'm just going to make it a dictionary. So letter counts equals a dictionary. And then we'll say letter counts of tasks. We could do a default dictionary, but I'll just say if task not in letter counts, then task, letter counts of task equals 0, and then I have an S there. Okay, so this should work. So if the task, basically if the letter is not in the letter counts, then we'll make its count equal to 0, and then whether it's in it or not, we'll add 1. All right. Okay, that's fine. All right, and then we'll say max heap equals so we could say so we want the value key for key value in letter counts dot items. Perfect. All right, so now this is our heap, and then we want to max heap. So we'll say heap queue dot heapify max heap, but this will do it the minimum. So I think we want to say negative value. All right, so this will give us the max heap here. Okay, get count of every letter. Create max heap. All right, so now with our heap, the algorithm itself is we want to. So let's try it with the version of making 2 heaps. So what we want to do is pop. So we want to heap queue dot heap pop. Let's just pop it from the list, and then we'll say like temp heap. I don't think I need that. Okay, so temp heap. All right, so the max elements. So we want current to go down by 1, and we need an answer somewhere. So say result. We want results to go up by 1 because that's 1 action. So this goes down by 1. Result goes up by 1. And then we can say temp heap dot heap push max elements. I think I'll make it tuples instead. So what we want to add is max elements of 0. So that's the count, and it is negative because it's a max heap, so we want to add 1 to it. And max element of 1. So now if I print temp heap, and alright, so let me just see if everything worked as planned. Alright, and then we want to print I didn't pass the so I have to say temp heap dot. So it doesn't work. So it's a list print type max heap. So they're both lists. Alright. Is there a way to create an empty heap? That's basically what I want to do. I mean, I guess what I could do is just say temp heap, and then I could just say that for now, I suppose. Alright, so we popped this and then added 1. So that looks good, and then we want to keep doing that. While max heap Okay, I have a question. So if can I say so if I say I equals 0, while I is less than length of max heap, then I say I plus equals 1, can I index max heap like this? Print max heap of I. Yes. Alright, so I think I'm going to do this instead. Or well, if I say 4 elements in max heap and then I modify the heap while I'm looping through it, does that... Let's try this. So for E in max heap, print E. So this should work. Yep. But what happens if I say also max heap dot heap push I don't think it works like that actually. Heap q dot heap push max heap, and like -5 is easy or something. Okay, that's not what I was expecting. Oh, it's because I did a list and not a tuple. Is it infinite loop? Okay, so it's infinite loop. All right, I'm just gonna loop through it and try a visited set. Could that give me an infinite loop though? No, I think it's probably fine. So we'll say visit equals a set, because we'll only increment I. Okay, so we'll say while I is less than length of max heap. So my goal is I'm going to try to add it to the same heap. And just like keep going. Okay, so while I is less than the length of max heap, we want I to go up by 1. So if okay, so let's get the max element. So if max element, and also what we want to say is visited dot add max element 1. So the letters. So this will be letters we've seen. It says to do it in O1 space though, which I'm definitely not doing. So I guess you could do it in place. Anyway, let's just try to get something. So max element of 1 in visited. I guess we'll say if it's not in visited, then we want to do all of this. Is this algorithm like... I think it actually might be M still, because you basically do something for every element, because you're always taking it down by 1 every time you visit it. So I think even though there's 2 while loops here, it's still M. Okay, so we pop the max element. If it's not in visited, then we want to make C go down by 1 and result go up by 1. And we also want to add it to visited. And we want to push it back in the heap. Except we want it to be this tuple. Alright, so for now, let's just do this. Alright, then I goes up by 1. So this should, so it'll, invis to just do nothing. And we can honestly just go until c equals 0 also. So while I is less than, and then I could put like, or c is greater than 0. Because when it equals 0, then we can restart it. Okay, let me see if I get any syntax errors. Runtime error. Alright. So this is all good. I don't need this, don't need this, don't need that. Okay, so this part's good. Prints. Okay. Popped max. C is not associated with a value. Okay. Okay, so we popped it, added it back, popped it, added it back, and then. So let's print results, and let's print C. Okay, so we did two things, and then C equals 0. Okay, well, I think what we want to say is, okay, so there's this. So there's two stop conditions. So if C is so if C is less than 0, then that means we can like break, because we should have another loop up here. Okay. So we don't want to add it back if it's 0. So if new element of 0 equals, I guess we'll say does not equal 0, then we can add it like that. All right. So we're missing the part where we add the idle. So this is how many operations, but we don't do the end part yet. So when it's empty, here we want to say that, actually here, we want to say that result plus equals whatever we have of C. And if C goes into the negatives, then we want to just break and reset. So I have res equals 6 now. All right, let's see. Okay, so we pop the max element, add it back as 1. And then we're in the outer loop. We should not be in the outer loop. C break. Okay, so that means if this is not breaking, then it means I is less than. I wonder if this has something to do with it. If it is invisited, then we just want to add it back, right? So if we pop something and it's invisited, then yeah, I think that's kind of a problem. So we pop it, add it back, and then we get an outer loop. Oh, no. This is not the outer loop, my bad. Bad debug. Okay, so add it back, pop it, add it back. Result equals 2 and C equals 0. So why did we break? We broke because we went through everything. Yeah, that sounds right. And then, so the outer loop now, this is our new one. That sounds right. And let's see here. Print added C to res. Oh, so, Okay, so pop, add it back. And now, when we're done, so let me trace that. So if we have 2x, 2y, like this. So if we do that, now current, so n equals what? 2. So it shouldn't go down yet. So maybe we should say C equals n plus 1. Added 1 to res. Now this should not be true either when we add 2 to res. Okay, so this part looks right so far. Then we have this. So we pop it. All right, so this part is incorrect. We should not add back. Oh, okay. Well, okay, so we New res is 3. We've done 3 actions. 1, 2, and then we had to wait before we could go back to the outer loop. Then we pop -1. And now it's telling me that we added 2 to res. Max element. I wonder if this is causing anything. So I don't know why it's doing that. Oh, it's because I see. So when we pop it, so maybe instead of is it possible we could say for element in Maxi? Do we ever use I? We don't even use. Does this break it? Okay, looks good. Then we pop it. Yeah, so I just don't know why it's ending there. So when we go to the outer loop, so we pop the max element. It's not invisited. Oh, right here. Popped max element. And then it exits. Yeah, so it's exiting prematurely. Alright, so I think I need a better condition than what I currently have, because it doesn't make any sense. So I wonder if the temp heap thing was made more sense. Because what I really want to do is just do something for every item. But it's tricky when we're like popping and stuff. I don't know. Should I say temp heap? Heap is empty list. So maybe instead of adding it back right here, we can instead say we'll add it to temp heap. Okay, I think this might work. This is not going to work, but I think eventually we might get there. Yeah, that's fine. Just get rid of this for now. So for elements in max heap, we're gonna pop an element, and we don't need this visited set anymore. So we're just going to pop it and add it back. I mean, this might be a waste of time. We might be able to say if max element of 0 plus 1. So this is the equivalent of saying if it does not equal 0. So if it does not equal 0, then add it back. Add back a new tuple. Max element like that. Why is it only doing... It must be because we're popping it. Okay. What if we say L equals length of max heap before we start? And then we say while I is less than L. And every time we want I to go up by 1. So it will have to run this many times. Okay. So now that seems to work. Alright, so max heap, and then we also want temp heap. I want to see what this even is. Empty. I'm just going to have it run for 5 times. So while j is less than 5. Just so I can see. Okay, temp heap is equal to this. So we want max heap. So here... So if it's empty, then we want to say max heap equals temp heap. I don't know if that'll just do a reference. Looks like it. Can I copy it? Alright, let's see. Okay, so this is a good temp heap. And then it instantly goes here. Oh, because we need to do it up here because L was 0. Okay, now we pop it. And then it's empty. So we want to check when we pop something if so when we pop an element, if temp heap is empty, then print final res. So shouldn't it be empty here? Added 1 to res, new res. Alright, I think I need an idea of what these look like. Need an indent, that makes sense. Okay. So that looks good, that looks good. This looks good, pop that, this looks good. Okay, temp heap. Yes, okay, but so when we do this, we also need to say that temp heap is empty again. Okay. So that looks good, and then here we switch it, and then we pop it. Okay, so this is incorrect, so we pop it, then we pop it. So I think what we can say is if they're both empty, so if they're both empty, then that's our final answer. 5. Let's see what it says here. 9. I mean, and then we could definitely clean it up. I don't expect this to work fully. Yeah, okay. So here we have n equals 1. So let me see what's going on here. Okay, so 2 A's, 2 B's, 1 C, and 1 D. 2 A's, 2 B's. All right. Am I not heapifying it or something? No, actually it looks fine. It's always popping the max element. Okay, so let's trace it. So we pop 2A. Alright, so we pop 2A, add 1A to temp heap. So this looks good. That's what we want. Oh, we don't have the C break. We don't have the C break. Okay, so in this example, we have -2, or let's just say 2a, 2b, 1c, 1d, and c equals 1. Alright, so we'll pop this, and that goes 1a. So c being 1 means there has to be at least one action in between, right? Yeah, it's separated by at least n. So after we do that, c goes down to 0. And then we do this, and then it's 1b. And now, so c is down to 0. Okay, so in this case, right here, so after we pop an element, and c goes down to 0. So now what we want to do is just restart the whole thing. So if we pop an element, I mean, we could say right here. So if c is less than 0, we want to combine we want to break. And what that will do is go down here. And what that will do is go down here. So in this case, it will add a -1 to our result, which we do not want. So this is very scuffed, but I'll just put that there for now. And what we want to do is combine these two into one. Okay, so if we make max heap null, all right. So we could say while max heap heap q dot heap pop max heap, and then we want to add that element. So heap q dot heap push temp heap. We want to add whatever element that is. Okay, so let's say here C break, and then we'll say basically this part. All right. Getting a text, sorry. All right, sorry about that. So we popped that one. So maybe we should check it up top. So C break though, assuming that it was just max heap was D. And so it does seem to work, that part of it, but we do want a C break earlier, I believe. All right, so C equals 3. We're gonna pop it, so that's one action. Pop another one. Now we're, sorry, wrong one. So C equals... So I said C equal to 2. Did I say if it's less than 0? I feel like I'm doing two things. I'm adding 1 here and then also saying if it's less than 0. Okay. All right, so I'm at over an hour. So I think it's probably just diminishing returns at this point. I think I could get it, like if I just keep doing this. But I think I'll probably just benefit the most from just looking at this solution and moving on. I'm just understanding the solution. Yeah. So I'm glad I was able to kind of put together how this one might use a heap. I think I was kind of on the right track. I think I'm very much on the right track. I just like my logic is really inefficient, but I think the idea being like you pop. I think the solution is probably gonna be like you pop it from the heap and add it back to the heap. But I just needed a better stop condition. So you should like pop it back, add it to the heap, and then I was thinking once you do every, like once you visit every element in the heap, then you would stop, but I was having issues with that because I don't know, basically what it came down to is I don't know how to ensure that you visit every element in the heap if you're modifying the heap as you're going through it. But yeah, I kind of had the right idea. That was just kind of stumping me, so I was going through all these like weird logic things that were just kind of confusing, getting really messy and convoluted. So yeah, so that's today's episode. So to recap, at the beginning of the episode, I solved subsets 2, but I did it in n log n times 2 to the n. So I think for this episode, a takeaway is I need to make sure to definitely look at these solutions and understand them for permutations and all the similar ones, or sorry, backtracking, all the similar ones like that. And same with heaps. I'll definitely look at the solution of this and just kind of make sure I really understand the solutions and learn from them, because I think that will kind of help me increase my skill a lot. And maybe at this point I'd benefit a little bit more from kind of learning instead of just doing. So that's takeaways for this episode. Yep, thank you all for watching. Today was day 23, I believe. So I'll see you tomorrow for day 24.